Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is Lecture 7. We're going to be talking about the first introduction to one of the core concepts in this class, namely that of random variables. We're going to focus on two particular examples today, although I'm going to talk about random variables in general to start. The two important examples for today are the binomial random variable, which you should think of as anything which involves this sort of choose notation. The second key example is going to be that of geometric random variables, which are going to be things of the form q to the n minus k times p to the, q to the n minus 1 times p, which essentially counts the probability of there being n failures before your first success. But let's get to the broader picture first. Up until now, we've been talking about essentially probability of events, sort of in the abstract. These are things like, what's the probability that it's going to rain today, given that it rained yesterday? Now, of course, these are kinds of problems we address all the time. But more often than not, we tend to look at probabilities of certain events occurring where those events are essentially indexed by numbers. So, for example, you might ask, what's the probability that out of 10 flips of a coin, I get 3 heads? So they were interested in the number 3, which counts the number of heads out of 10 attempts. So let's go ahead and carve out a little more general notation here. So this is, before, I should say up to now, we've been discussing probability events. And then today and going forward, we're going to be talking about the probability. We're studying how numbers vary according to some random process. So we're going to be summarizing or studying numbers. And you think of numbers as being, either integers or natural numbers or just anything that's a part of the real line that vary according to some random process or experiment. All right, so let us go ahead and isolate a definition. And I think it's going to be good to have a picture that accompanies this definition. But let's first, let's get at what we're defining. So a random variable is a function x from our sample space omega to the real numbers. So again, this is our sample space. And these are going to be the numbers that vary. According to what outcome we're looking at in omega. But we require some further properties. It's not just any old function. Rather, we want to have further the probability that if I want to see if x is in a certain range, that probability needs to be well defined. So this is a function such that whenever I look at a pair of numbers, let's say a less than or equal to b, the probability that X lands between A and B needs to be well defined. So the cartoon you should have in your head is that, I've got this cloud of possibilities, omega. I've got my my real line. These are the numbers which are going to vary according to omega. And I'm looking at my experiment or process that produces numbers that vary inside of R. So this is X. And moreover, when I look at, let's say, an interval like this, A less than B, and maybe that interval includes some numbers that we like 1, 2, 3, and so on and so forth, that when I sort of pull back or ask, well, what set of events or outcomes landed inside of this interval, we get the following. So looks like some subset here. And this is going to be the set of events where X is in my interval, let's say AB. And so ultimately what we're then going to try to study is we're going to compute the probability of this. And that has to be some number between 0 and 1. So basically, we're going to now carve out events indexed by numbers inside the real line. That's going to define some set of outcomes that put us in that bucket of numbers. And then because we have a sample space with a notion of probability on it, basically a probability measure, then by computing, something like the area or the number of events that are in this region weighted by their probabilities, that's going to be the probability of this event that X lands between these pair of numbers. This might seem abstract, but let's get down to a few examples. I do want to mention two special cases of this definition before we move on. So the first definition, this is going to be the thing we focus on for most of this the next several lectures. It's going to be the following. So I'm going to say that a discrete random variable is one where the set of possible values, so where the range of X is either finite or more generally countable. So we're going to think of this as like the natural numbers, 1, 2, 3, so on and so forth. And by contrast, a continuous random variable is one where the range of X is continuously varying. Of course, it's bad to use the term that you're trying to define with the term itself. So the more technical language is the following. When the range of X is uncountable. And this is where this whole notion of, we want the probability to be well-defined actually comes into play. It turns out to always be well-defined in the discrete situation, at least definitely in the finite case, but in the continuous setting, there are some peculiarities. And this is really illustrated by one of our most canonical examples of a continuously random variable. So I'm going to look at an example here. So imagine we're looking at a dartboard where we've got this alternating regions where there's little colors here that alternate. band here as well. And this whole idea of like, suppose I want to throw a dart at this dartboard. So, bing. So if I throw a dart, I can look at its height as its y position. And that's going to be the random variable that I assign to the outcome of throwing a dart. What is its, let's say, height from the floor. Now, if you assume that you can always hit the dartboard, but let's say you're not very good at aiming, so meaning you can hit any point on the dartboard uniformly at random, then if I were to ask you something like, okay, what's the probability of y being inside of this range A to B? Well, one thing you could do is just look at the region of the dartboard that corresponds to that region. And in this case, I would then say that, oh, the probability that y is between A and B is given by the area of this region, of course, divided by, let's say, the area of the dartboard. Of course, this sort of normalization factor is just a byproduct of the fact that probability can never be greater than 1. And so you need to make sure that you normalize by the total area of the dartboard. Okay, so we'll get into the particularities, how to deal with continuously random variables like those that come from throwing a dart at a dartboard later in this class. Right now, we're still just sort of making our way through discrete probability and understanding that more precisely. So let's get at this, maybe our canonical discrete example, at least one that will really allow us to understand what's going on here. So let me go ahead and call this the sort of 2-coin example. And the basic idea here is we've got these 2 coins. Maybe we've got George Washington's face on this one. And we're going to assume that these are fair coins. So probability of heads or tails is a half for both of them. All right, so suppose we have 2 fair coins. This means that the probability of heads is equal to the probability of tails. That's what fair means. And now let's suppose I toss both of them at the same time. Now, what are some interesting quantities that I could attach this experiment of tossing 2 coins? Well, one candidate random variable, so it's a number, a quantity that I can attach to this experiment, is counting the number of heads that I get. So let's and I'll call this kind of curly h, just to indicate it as separate from individual heads and tails attached to each coin. So let curly h equal the number of heads when we toss both of these coins. So the first thing you want to consider is, what is the range of h? So clearly, h has to land between 0, 1, or 2. Can't have more than 2 heads because there are only 2 coins, and can't have fewer than 0 because that doesn't make any sense. How do we compute the probability of each of these sort of events carved out by which value h takes? It should be pretty straightforward, but let's go ahead and go through the motion. So let's say, what's the probability that I have 0 heads. So I want to think of this as probability of 0 heads. Well, if I, let's say, name events, like the first coin is a tails and the second coin is a tails. And let's say I go ahead and use this as here's coin 1 and here's coin 2. I could say that this is the same thing as the probability of coin 1 being a tails and the probability of coin 2 being a tails. All right, so that's exactly what's meant by each of these symbols. This is the event where coin 1 is a tails, and correspondingly, this is the event where C2 comes up tails. Now, we've made some assumptions that are very plausible, namely that the outcomes of each of these coins are independent, meaning what happens for the first one doesn't affect what happens for the second one. So by independence, we can conclude that this is the same thing as just computing the probability of these two things multiplied. So here we're using by independence. Which, again, assuming these are ordinary fair coins, this is a half times a half, which is a fourth. All right, so that was super easy. Let's go ahead and do the next easiest thing. So dually, I could say that the probability that I have 2 heads is the same thing as the probability of T1 not happening and T2 not happening. Now, what's that? Well, again, by independence, it's the same thing as that, which is the same thing as, let's say, probability of the first coin being a heads, second coin being a heads, which is, again, going to be a fourth. All right, so we can stop for a moment and consider, well, I've already calculated 2 of the possible events associated to the 3 possible outcomes for H. H can be 0, 1, or 2. I know what the probability of 0 is. I know what the probability of 2 is. So I can just compute the probability that H equals 1 by taking 1 minus the sum of these 2. So that's a fourth and a fourth. So this means that the probability of H1 has to be a half. But let's see how we would compute it directly in case you didn't think of it that way. All right, so the probability that H1 equals 1. So how do we write this out symbolically? You might do something like this, which could get a little confusing. So let's say I look at the probability that the first coin is a heads, or the probability that the second coin is a heads. But I know that this is going to double count, or it's going to include something I'm not trying to count, which is the probability that H1 and H2 both occur. So I have to subtract off the probability of H1 and H2 occurring. Right, so I'm just going to make a little remark. If I want to know the probability of H1 being greater than or equal to 1, I could just compute this as the probability of H1 union H2, which we know by the inclusion-exclusion principle is the probability of H1 plus the probability of H2 minus the probability of H1 and H2 happening. But that's not what we're computing here. Here we're looking for equals, not greater than or equals, which is happening here. So let's go ahead and work this out. So we've actually already written out half of what we need to. and we can already use independence. So this looks somewhat confusingly like probability of H1, first coin being a heads, second coin being a heads. And then maybe somewhat weirdly, I end up subtracting it twice. So minus 2 times probability of H1 and H2. Now, probability that one coin is heads, well, that's obviously 50-50, right? It's 1/2. So 1/2 plus probability of the second coin being heads, well, that's also a half. So if we didn't subtract things off, we would have already mistakenly concluded that the probability of this happening is 1. It's not true. So now I need to take minus 2 times, well, this is obviously a fourth, right? 1/2 times 1/2 by independence. So this ends up equaling a half in total. So the probability of H1 equals 1 ends up being a half. And here we had a fourth for H2, and back here we had a fourth for H equals 0. So what's another way we could have done this? And this is going to connect back with the perspective I was trying to give of a random variable as being a function on this outcome space, omega. So here's an alternative way of thinking about it. So alternatively, I could have drawn or written down all the elements in my set omega and just counted the number of ways in which I got one heads. So let's just write down, what is omega? So I'm going to use this sort of coordinate pair to refer to what was the outcome of the first coin, coin 1, and what was the outcome for the second coin, coin 2. All right, so I could have, I've already considered the case where I have tails, tails. This is coin 1, and this is coin 2 outcome. I could have tails, heads, heads, tails, heads, heads. So notice that this right here corresponds to the event where H equals 0. This corresponds to the event where H equals 1. And this corresponds to the event where H equals 2. So again, by looking at all the possible values of my heads counting random variable, I actually partition my space of possibilities omega into these separate chunks. There's another visualization of this that's pretty useful. Let me draw it here, and this definitely works when we have an experiment which is product of sort of two things happening. So obviously I've got my coin 1 outcome, and I got my coin 2 outcome. And again, this is going to be another way of thinking about omega. But I know further that each of these two factors has two possible outcomes. There's the tail and the heads, or there's a tail and a heads. And so what we're looking at in each of these situations is something like, let's say here, this tails, tails, this corresponds to the event H equals 0, because this is tails, tails, which we already calculated has a probability of a fourth of occurring. By contrast, if I, let's say, look at my green event here, maybe go ahead and box this in too. If I look at my green event here, this corresponds to the region where H equals 1. And I see already that this is, all right, this is tail heads, which has a probability of a fourth. This is heads, tails. This is probability of a fourth. And so by summing these, tail heads plus head tails, I get a fourth. And then I also have this this probability here. So that's sort of a nice visualization. There are going to be situations where this visualization fails. So imagine we're tossing 3 coins. Then you would need to have a third axis. And suddenly this representation is not as useful. But we're going to go to a representation that is shortly. But I want to revisit, up till now, we can compute probabilities in these sort of settings with a fair coin, for example, just by counting the number of ways that something occurs. And here is easy to see. Well, there were 2 ways for this event happening, so it's twice as likely as either of these events. That's not always true, though. And this happens especially in situations where there's sort of bias. So you're flipping a bias coin, head or tails. Or in another situation, which we have discussed or touched on in class, which is maybe let's go to a yoga class where there are only 2 people. So it's a small class. So here's an alternative example. And this illustrates, this is going to be an example where counting is insufficient. So imagine we go to a yoga class, and we're going to use the following facts, slightly altered from what the truth is here. So if you go to a yoga class, then the probability of being a man in a yoga class is about 25%. And the probability of being a woman is about 75%. So again, we'll just represent that as a fourth, and this is 3/4. So what if I defined a random variable associated to a class where there are 2 people, and I want to count what are the number of women. So let W people the random variable that counts number of women in a 2-person yoga class. Again, we're not going to assume that the people going are friends or anything, so there's no sort of correlation. We get to use the assumption of independence. Well, now this is fairly easy to document, and I'm just going to go ahead and jump to the picture of our sample space here, but where I'm scaling the area according to the probability of each event. So let's imagine we've got, again, so now we've got person 1, instead of coin 1, we have person 2. Well, let's say they could be a man or they could be a woman. But we know that the probability of each of these events is sort of scaled to be a fourth of this other probability here, or at least third as much. So this looks something like this. So the probability of no women ends up being a 16th. And the probability that the first person's a man and the second person's a woman, so this is man, woman, well, it's going to be 3/16. And then similarly over here, so this is going to be underneath the woman, man, 3/16. And the probability of 2 women is 3/4 times 3/4, which is 9/16, which is over a half. So this illustrates a situation where if I were to write down a table of possible values, W, and the probabilities, so the probability of W equaling that, I would get a 16th, 3/16, and 9/16. Oh, sorry, I that doesn't add up to 1. So I need to sum these two. 3/16 plus 3/16 is 6/16. So we call this right here the probability mass function. Associated to this random variable, PMF. PMF. Very good. All right, so what was happening in both of these examples, either the 2 coins or the 2 people in class, is that we had some total number, in this case 2, and every try or every person was sort of independent in one of 2 possible outcomes. Ultimately, what these variables H and W were counting is they're counting the number of, let's say, successes, or at least number of ways in which one of the 2 events happens. And we sort of saw this weird quirk where you have to, even for a problem that doesn't feel like it has order, like individual people or maybe indistinguishable coins, we still had to count the number of ways in which you could have 2 things happening. You could have a man and a woman, or a woman and a man, or a heads and a tails, or a tails and a heads. So let's go ahead and outline what's the general principle here. And this leads to one of the really fundamental probability distributions or random variables that we're going to study in this class. So this is known as the binomial random variable. So write this in big letters, binomial random variable. And what this binomial random variable is counting is it's counting the number of successes out of, let's say, n tries. So suppose, let me just say this, I'll just say it counts the or let me be even more precise. This tracks the probability of k successes out of n identical independent tries. And so we'll use the letter S sub n to indicate this random variable. So this will be our S sub n. It's going to be. And so what's the general method for determining the probability of k successes out of n tries? And the important thing here is we don't care necessarily about the order of these successes out of the n tries. We just care about the number of successes out of n tries. So you can do this basically in 2 steps. So how to compute the probability that Sn equals k. And again, we have to acknowledge that Sn can take in any value between 0 through n. You could try n times and not succeed a single time, or you could try n times and succeed every time. And any value in between is possible. So how to compute this? How to compute this probability? Well, it's basically 2 steps. But eventually we'll package these 2 steps into a single formula. So in the first step, we can compute what's the probability of, let's say, succeeding k times in a row, and then our last n minus k attempts are all failures. So I would say compute probability of of a success, all the way up through our kth success. And then we fail on the k plus first try, and we keep failing up through our nth try. Now, by independence, we know that this should be equal to the probability of S1 times probability of S2 up to the probability of SK. And then we need to multiply by the probability of failing, FK plus 1 times probability of Fn. Now, the assumption that each of these trials were independent was used here to turn this AND statement into a product. But this issue of identical, well, that just says that each success was equally likely and each failure was equally likely. But since both of those are the only options, success or failure, they need to add up to 1. So let's use some notation here. So we're going to call probability of success P, and we're going to call the probability of failure Q. And of course, P plus Q must equal 1. So it turns out, finally, that we can finish this calculation by saying probability of K successes in a row followed by N minus K failures is P to the K times Q to the N minus K. Now that's not the final answer, because we've computed here the probability of a very, very specific event. K successes in a row followed by N minus K failures. So now what we have to do is a little bit of counting. So now let's just count the number of ways of K successes out of N tries. Well, that's obviously N choose K. You think about it, right? You've got your N total tries, and now you just need to pick K successes out of those N possible tries. The way of doing that, number of ways of doing that is N choose K. So this gives us our final answer then. So the probability that out of N tries I have K successes, which is the same thing as writing P of Sn equals K, is equal to N choose K times P to the K, Q to the N minus K. This is sometimes called BNKP, because this is known as the binomial distribution at values N, K, and P. This is called the binomial distribution. And what it effectively tells you is the probability of each possibility for K ranging between 0 and N. All right, so I want to modify this question slightly and consider another related example. And this will give you an example where you can just kind of move directly to the final answer by using the formula. So here's an example. So imagine I've got my urn. And let's say there are 3 red balls and 1 green ball. 3 red plus 1 green. And suppose we're going to draw with replacement 10 times. What is the probability of, let's say, having 5 green balls out of 10 draws? Question. So that's the question. It seems basic enough, but now you need to figure out how to model it using the language and math we just introduced. So for example, I want to think of getting a green ball on a draw as a success. So here's the answer. Let's say drawing a green ball is a success. What's the probability of that success? Well, since we're drawing with replacement, that means I reach in, I draw it, look at the color of the ball, and I put it back, mix them up, and then try again. Well, we could see there's obviously only 1 green ball out of 4 in total. So the probability of success here is 1/4, and consequently the probability of Q is 3/4. And so now I can just say that, oh, the probability of out of 10 draws, there being 5 green balls, 5 successes, is 10 choose 5 times 1/4 to the 5th times 3/4 to the 5th. And that's it. Very easy once you get trained to recognize when this problem involves binomial distribution. Now let's consider a slight variation on this question. So let's consider a subtle variation. Maybe you think it's not so subtle. Maybe instead of asking a question like, I draw 10 times, what's the probability out of 5 of those draws I get green balls? I want to instead say, let's suppose I reach in, grab a ball, look at its color, and I keep going until I get my first green ball. So we have changed the experiment. So we're going to change the experiment. Draw balls with replacement until first green ball. Let's record, let's say T is the time or draw number that this first green ball appears on. So let T equal the draw number where first green ball appears. Now, this is one of those situations where this is a discrete random variable, but there's actually an infinite set of possibilities. Like you could be very, very unlucky, and every time you reach in, you grab a red ball. Again, it becomes increasingly unlikely, but it is possible. So the possible values for T well, you might get a green ball on the first try, or on the second try, or on the third try, or the millionth try. or, the 3 billionth try, so on and so forth, up to, but not including infinity. And you can just compute what's the probability that you get a green ball in the first try. Well, it's not so bad. Only a 1/4 chance, but still not as likely as getting a red ball. What's the probability that your second draw is a green ball? So here you have to assume that the first ball that you drew out of the urn was red. So what's the probability of that? That's 3/4. And then you now compute the probability of, once you put the ball back in, the probability that the next ball is green. And in general, you can kind of see what the pattern should be. So the probability that t equals k, in this case, is 3 to the 4th, 3 over 4, k times, k minus 1 times. And then on the kth try, we finally got our success. So we can write that more compactly as 3/4 raised to the k minus 1 times 1/4. So this actually gives us another random variable, which we call the geometric random variable. This says that the probability that your kth success, or your first success, happens on the kth try is equal to probability of failing k minus 1 times and then succeeding on that kth try. And so this is another fundamental example of a random variable. All right, so pretty much close to ending. I do want to show you one important variation on this problem where you change the hypotheses a little bit. So in this setting, we were considering where we took draws with replacement. Drawing with replacement has the effect of giving you independence, which means that you can compute the probability of these long sequences of events. So, and this happened, and this happened, and this happened, and this happened, into a product. Again, being able to turn ands into products is the definition of independence. So let's just consider the situation where got the same urn, but we don't replace the balls. And let's see if maybe you can predict what's going on. So some final words. Some final comments. So draws with replacement have the effect of turning, a probability of a sequence of events in other words, we can turn ands into products. So what happens if we draw without replacement? Maybe not the long way, but we need to sort of compute them using some conditions. That means we have to consider what happened before when computing the next thing. So if we revisit our example of 3 red plus 1 green ball in an urn, maybe let's draw without replacement. And let's consider the random variable, let R equal the number of red balls before the green ball appears. So again, first of all, recall that if I look at the range of R, well, my first draw could be a green ball, in which case I had 0 red balls appear before my first green ball. I could have 1, 2, or 3, but you can't go higher than 3 because there are only 3 red balls and we're sampling without replacement. Meaning once we pull a red ball out, that red ball is not going back in, and there are now 1 fewer in there. So let's compute. What's the probability of R equaling 0? Well, we already kind of know, right? This is you have a fourth, because that's the probability that the first ball we draw is green. Now, what happens if we want to see the probability that R equals 1? Well, it starts to look kind of like a geometric random variable. So we need probability that our first ball is red. So that's 3/4. But then what's the probability now that my next ball is green? So you want to think of this as the probability of green given that our first ball, let's say B1, was red. Well, I need to subtract from the space of possibilities, right? There's only 3 balls left and only 1 of them is green, but when you do the calculation, we end up getting that this is 1/4. All right, what's the probability that R equals 2? Well, we need a red ball, another red ball, but now there's only 2 out of 3 red balls, and then a green ball. And there's only 2 balls left on that third draw. One of them is green. And again, you do the sort of cancellation, you end up getting a 4th. And now what about the probability that the red ball, we get 3 red balls before finally drawing our green ball? Well, 3/4, 2/3, 1/2, and then we're forced 1 out of 1 for there to be that. And again, you do all the simplification, 3, 2, 1s, and this ends up equaling 1/4. So weirdly enough, when we drew balls without replacement and we asked what's the number of red balls before I get my green ball, this ends up being a uniform or a uniformly distributed and in some sense it has almost a feeling of what's the number of cards you need to draw until you get your first ace, assuming you're drawing without replacement. It ends up being very similar to that question of like, what's the probability that my second or third card is an ace? All right, so that's enough for today. I look forward to seeing you all in class.